This next series of video actually covers a large area. We're going to look at increasing and decreasing functions, what's known as the first derivative test. We're going to talk about concavity, inflection points, and tie in the idea of the second derivative. So let's look at specific learning objectives for these next several videos. Number one, I want to determine intervals on which functions are increasing or decreasing. I want to apply that first derivative test to help find relative extrema of a function. We've actually already done this. I've done it in earlier examples. I just didn't call it the first derivative test. We want to determine the intervals on which a function is concave up or concave down. So we need to actually define the idea of concavity. We want to find the points of inflection on a graph. So we also need to define what inflection means. And I want to apply what's known as the second derivative test to help find relative extrema of a function. So like I said, there's quite a bit going on in these next several videos. Now first, let's start with the idea of increasing and decreasing functions. A function is increasing on an interval if for any two numbers x1 and x2 in the interval, if x1 is less than x2, then that implies that f of x1 is actually going to be less than f of x2, which makes sense if I have a function that's increasing, something like this. And here's my x-axis. If I pick an x down here, x1, that's less than any other x2 that I pick. F of x1 is less than f of x2. That's true for everything on this interval. Now, the decreasing definition is exactly the same idea, only obviously if x1 is less than x2, so I have this left to right motion again, that then implies that f of x1 is greater than f of x2. So if it's decreasing, perhaps a function looks something like this on some interval. Clearly, if I take x1 less than x2, any x1 in the interval, any x2, as long as I have this left to right orientation, so x1 is less than x2, then f of x1 will in fact be greater than f of x2 anywhere in this interval. Now, a function is said to be monotonic if it's strictly increasing or strictly decreasing over its domain. Now, quite often we make reference to a specific interval, or we may limit the domain and say that over its limited domain, this particular function may be monotonic, increasing or decreasing. As an example, something like f of x equals the square root of x. That looks like this. That's monotonic increasing over its entire domain. Something like f of x equals negative x cubed, that would look something like this, and that's decreasing over the entire domain, where this domain is negative infinity to infinity, and this domain is 0 to infinity. So that actually leads us to the idea of a test for increasing or decreasing functions. So let f be a function that is continuous on the closed interval ab, and it's differentiable on the open interval. Now, this differentiable on the open interval, what that really tells me is that the curve is smooth on that open interval a to b. Everything I've drawn so far has been a smooth curve. If I have something that perhaps looks like this, maybe it's going like this. Right here is a cusp, and at that point the derivative is undefined. So if my interval is like this, a to b, this cusp exists inside this interval here, then this is not a smooth curve. The derivative does not exist, so it is not differentiable. The function is not differentiable on the closed interval. So I need something that is closed on the interval. So in other words, I need some type of smooth curve from A to B. Okay, so under those conditions, if f prime of x, if the first derivative is positive, it's greater than 0 on that open interval a to b, then f of x is increasing on the closed interval a to b. And the other situation here is if the first derivative is less than 0 on that open interval a to b, then f of x is decreasing on a to b. Now that really kind of makes sense when you think what a derivative does. If my interval from a to b, if my function looks like this, well, what's going on here with the derivative? The derivative, the slope of the tangent line, is negative. It's negative everywhere in this interval. And that's what's saying right here. On the other hand, if I have something from a to b that looks like this, then clearly the slope of my tangent line is positive, is greater than 0. So my function is increasing on a to b.